right, so we're going to keep this pretty casual. So if you have any questions, feel free to raise them at any time. But I'm here today to talk about Synapse Pipelines 360. So what I'm going to do is going to bring you in from a pretty entry-level, introductory presentation about Synapse Pipelines, but at the end, I'm going to have a series of slides about some best practices that you can use in your organization for things like data loading. So here's some of my contact information. Feel free to reach out to me at any time. All right, so we're going to start with what exactly is Azure Synapse Analytics. Azure Synapse Analytics is really a unified environment that brings together data ingestion, big data analytics, data warehousing, everything at cloud scale. So it unifies a lot of your data workloads as you have it today into one environment. So we're talking about your data scientists, we're talking about your ELT and ETL developers, we're talking about your AI groups. Everyone can actually come into one specific environment and get all of the workloads that they need to have done. So it's very much a unified environment that you don't have to have multiple UIs essentially to go into each different type of workload. So another thing that it does too is there's over 100 connectors to different types of data sources, even some that are generic. So when I talk about generic, it's things like ODBC connections, REST APIs, for instance. But there is over 100 connectors, even to a lot of vendor platforms, if you will. So the goal of Azure Synapse Analytics is not only to unify a lot of your data workloads, but it's to bring all of your data into one spot too. So you're able to have that end-to-end analytics view of your environment in one spot. Another thing, again, because Azure Synapse Analytics, again, unifies everything, a lot of the monotonous tasks, like if you have infrastructure out there that you're securing, 8 different services because it feeds into another one. What's really nice about Synapse Analytics, again, is they simplified this. So they have the model that essentially sits on top of Azure Active Directory. You secure Azure Active Directory, that's basically most of what you have to do is secure your Azure Synapse Analytics Studio. So a lot of your monotonous stuff that you have to do typically at the beginning of a launch is done fairly easily for you. So let's begin our story. And again, this is going to be a little bit of a beginner level as we start out here. But I want to talk a little bit about data ingestion. So data ingestion is typically the first thing that you're going to have involved when you're populating your data warehouse. So it can be performed in many different ways. It could be files being dropped by an SFTP server, could be external databases, could be batch processing, could be streaming data. So as I mentioned before, Azure Synapse Analytics has built-in connectors to hundreds of different data-bearing services, so external computes that you can actually tap into. So when we talk about data loading, some of the terminology that you're going to hear a lot is the concept of ETL and ELT. And let's talk about that just a little bit because there is some subtle differences. So ETL is extract, transform, load. They have, again, a lot in common, but extract, transform, load pulls the information from the remote systems and essentially performs the cleansing and the transformations right there in the same pipeline. Loads it right into your data warehouse without, when I say data warehouse, a lot of people actually have the concept of what's called a data lake, which is essentially where you land your first versions of files, if you will. So ELT, on the other hand, will extract data from one or multiple services and load it directly into your data warehouse without any transformations at all. So ETL does the transformation as part of the pipeline. ELT just grabs that raw and sticks it directly into the data lake, so without modifying it or touching it at all. So one of the reasons why you want to do this is ELT is because when you have a data pipeline, typically that riskiest part of the communication between your data warehouse system and whatever you're connecting and pulling data from is the most fragile, most error-prone process. So the attractiveness of the ELT, where you're actually grabbing everything in its raw format and dropping it into the data lake, is that after you do that initial copy over, if there's anything that, like processing problems that happen down the pipeline, you don't have to actually go back as far as grabbing that source data again. You've already landed that in your data lake. So one of the use cases, I guess, that I like to bring up is, especially when you're doing your initial development, that if you have a problem inside of your pipeline and you have an error, how much of a pain in the butt is it if you have like a 2-hour process to gain that initial data, raw data from your source systems into your data lake and have to repeat that for every error that you're debugging, right? So that's a pain in the butt. So what's really nice about the ELT process is, again, is if you drop those raw files into your data lake, every time something happens, you already have that locally to your data warehouse that you can go ahead and try something new, and especially during the development of your pipelines, that can be very beneficial. So there's a couple different ways of landing the data. Obviously, we do recommend the data lake approach, meaning that you do want to store your files in certain levels of refinement directly into your data warehouse, whether that be inside of, in this case, Azure, so ADLS2, like Azure Storage. Some people like to have different levels of refinement, so that's a typical pattern that you'd see inside of any data warehouse implementation. So one of the most common ones is definitely the Databricks approach, where they have bronze for raw, silver for refined, and gold for queryable. I'm using actually one, I think I have it as raw, refined, and then of course gold for my actual data warehouse. All right, so that is just kind of a concept of, data loading. So that's where data pipelines comes in the focus of this talk. So with Synapse data pipelines, what you're going to see is a few different constructs that are at play here. So the pipeline itself is made up of different types of activities. So the activities could be stored procedures, they could be copy data activities, they could be Spark notebooks that execute code. So those activities essentially consume or produce data. Now, typically, those will also utilize a concept of a data set. And the data set essentially is a pointer within your source compute to the data that you're interested in processing. And then the link service is that final piece of the puzzle here. And the link service is essentially, the way I like to think of it, is as your connection strings to your external compute. So let's talk about link services. As I mentioned before, link services essentially establish that connectivity. So again, over 100 different connectors. You'll see things for SQL, Oracle, Netezza, hundreds of different connectors, even Snowflake if you wanted to. So the link service itself, again, is that connection string to external compute. One of the things that I'd like to promote here is that those of you that are familiar with Azure services are probably familiar with Azure Key Vault. And Azure Key Vault is available to ensure that your secrets stay secret. So people like your developers, for instance, do not need to have access, or credentials, I should say, to the database itself. So what a Key Vault does is it allows you to put those secrets and store them away and actually have Synapse utilize its identity to pull, as in like a read-only format, if you will, the credentials that you'd be using. Another thing to note is that if you do want to use Key Vault when establishing your link services, you need to actually first add it as a link service itself, using the managed identity of the workspace and access policies essentially to list and get those secrets. Another thing too to keep in mind, if you're accessing different storage accounts, for instance, as well, you also have the ability to leverage the managed identity of the Synapse workspace to secure things like your storage accounts, for instance, for the pipelines to have access to what it needs. The next talking point is going to be the integration data sets. So integration data set is that specification of the data. When working with a data pipeline, typically when you're moving data from source to destination, it's going to be described in the context of an integration data set. And a data set is just metadata. So when you define a data set inside of Synapse, it's not actually going to contain actual physical data. It's just going to point to a specific location, for instance, with a specific schema to data that is going to be utilized by the pipeline. Another part of the integration data set is it needs to be associated with a link service. So in this case, say you had an Oracle server and you want to pull, for instance, a table inside your Oracle server. You would have a link service that would essentially have your connection string to your Oracle database. And inside of the data set, essentially what you're going to do is point to the specific table that you're interested in processing. So that is essentially just all metadata. It's essentially a pointer construct to the data that you're looking to use inside of your pipeline. So the pipeline itself, as I mentioned earlier, is made up of different activities. Pipelines are really where the magic happens. So when we're talking about any type of data ingestion or refinement, they typically, well, they always are part of a pipeline. So data pipelines are created using various activities. So these activities could be copy data activities, stored procedures. As you're going to see here, you can have also different control structures. So you can have for loops in there. You can have switch statements, for instance. So another thing, too, that you could use is you can use it for branching conditions, looping, or wait operations. What's really nice, though, is when you're defining these pipelines, you're not actually writing any code, that you're using a visual canvas essentially to compose the different activities and control structures directly inside of a visual UI. The integration runtime is another important piece of the puzzle, and the integration runtime is essentially where the pipeline runs. So there's 3 different types of pipelines that are available today. One is the Azure integration runtime, and that's if you're connecting to different cloud data sources. So if you're connecting to Redis or to Snowflake or other type of cloud computing, typically you would use the Azure integration runtime to make those connections. The self-hosted integration runtime is actually a fun one. So a lot of people have a lot of on-premises type data sources that they want to include within their analytics. So the self-hosted integration runtime actually does a handshake. So there's a certificate-based handshake. But essentially what you're given here is a pipeline, I guess you could say, that would tap into your on-premises network. So this all runs over port 443. So it's typically one of those ones that are already open inside of your firewalls. But what's nice is that you're able to run Azure pipelines and pull data from your on-premises data sources directly into Azure Synapse Analytics in the cloud. You have the ability to scale it, so it currently has support for up to 4 different nodes, and it has compute for data movement and activity dispatch. One of the things that is missing here, and one of the concepts that we're going to go over in the demo here, is that the data flow activities currently cannot run on a self-hosted integration runtime, but you can run just, as long as you're not using a data flow activity, you can essentially run basically everything else. Azure SSIS is a new kid on the block, so a lot of, again, when we're talking about legacy infrastructure, we have a lot of investment, I guess you could say, into SSIS workloads when we're talking about like data warehouse type activities. So the Azure SSIS integration runtime was brought in to essentially allow you to lift and shift your existing SSIS workloads into Azure Synapse Analytics. So here's just again, I'm a big fan of visuals. So this is an overall picture of what a typical Azure Synapse pipeline looks like. So on the left here, we have the source, which is your external compute, the data that you want to ingest into your data warehouse. So that is typically defined with a connection string and an integration data set. And then on the other side, we have the destination. So that, again, looks pretty similar. You have a link service to where that data is going to go, defined by an integration data set. And then the destination compute can be like your storage account, for instance, or it could be your actual data warehouse database as well. So those are essentially just a high-level picture of what a data pipeline looks like. The last piece of the puzzle, again, is the triggers. So a lot of times, of course, you don't want to have your people sitting at their desks manually triggering these things. So you want to establish pipeline triggers either on a schedule, so you can say, like, every Tuesday at midnight, I want to run this data pipeline. You can do it event-based. So this is one that I actually use pretty heavily, where we might have an SFTP process that will upload a variety of files, and you can actually have pipelines trigger based off of the storage event of a file being dropped inside of a storage account. So we have an SFTP server essentially fronting a storage account that will, in turn, trigger an event-based pipeline based off of files being dropped there. There's also tumbling window, which essentially runs on intervals. The good thing about that one is that you're still able to retain state. And then, of course, on-demand is always available to you. So if you want to run one-offs, or when you're doing your initial development, a lot of times you will utilize the on-demand trigger. So let's go ahead and dive into an actual demo of Azure Synapse Analytics. So let me go ahead and find my, boom, there we go. So this is, again, that unified UI. So everything that you need to do when it comes to data workloads, you can do specifically within this one spot. So on the left, you can see a series of hubs. We have a home hub, a data hub, a develop hub, integrate, monitor, and manage. And you can see there's also things like integrations that you can have into your Power BI workspaces, for instance. So you don't even need to use Power BI desktop if you don't want to, or use the web tools that are available in Power BI separately. You can actually develop your Power BI reports also directly within Azure Synapse Analytics if you see fit. So obviously I have pre-deployed an Azure Synapse Analytics environment. So let's go ahead and take a look at the scenario that I've implemented here. So this is a proof of concept scenario that essentially what it does is it uses the Tmdb Api to pull movie information, because, you know, what's Star Trek without movies, right? So inside of this full movie pipeline, you can see that I have different activities in here that are composing the workload essentially to ingest, curate, and populate data into our data warehouse. So the first activity you see here is an execute pipeline. So pipelines are nestable, if you will. So execute pipeline is essentially a activity where you point it to another pipeline, and it essentially runs, it's like pipelineception. I don't know how else to put it. It's nice and it's interesting to try to explain. But at the end of the day, what this does is there's actually a couple different steps. So I'm going to dive into this first execute pipeline activity. You'll see, of course, then we have another one. So yeah, try not to nest them way too deep, though, because then it can get a little unwieldy. But you'll see that we have, again, a couple more execute pipelines, and then we have two different activities here. One's a notebook, so this is using Python Spark code, And we also have a data flow, which is another graphical way of moving data, if you will. So in a nutshell, what we're going to be doing is there's a couple different steps. So part of the Tmdb API is there's a discovery endpoint. This is all REST-based. So it'll go through the discovery endpoint, retrieve a bunch of header information, if you will, from their movie API, their discovery API. From there, we're going to refine that. So we're going to land it as JSON. From there, we're going to refine it. So typically on levels of refinement, what we recommend is using a Parquet format. So land raw, just as raw as can be. So if it's JSON you're pulling, go ahead, dump that as JSON inside of your data lake. But when we're talking about refinements, typically what you're going to do is you're going to utilize, again, it's kind of like I don't think it's considered an industry standard, but it pretty much is industry standard of using Parquet. And there's a couple different flavors that you can look at for that as well. So we're going to get the header information. We're going to do some minor transformations and store that in Parquet. Then there's a secondary details endpoint. So again, this is another Tmdb REST API. And I've implemented code here to essentially pull movie details based off of the movie header information that we retrieve. So I'll have a movie ID essentially, call the details, store that data in raw as well for movie details, and then of course refine that to Parquet. So this is just the raw ingestion part. Another thing that you're going to note is that there's parameters involved. So the full movie pipeline here, you can see that we have no variables on it, but if we come in here, we have an API key as well as company IDs as parameters. So you're able to set parameters in and out of different activities. So this one's parameters going directly into the pipeline. You also have the concept of variables, which we'll get into here in a little bit. But let's go ahead and take a look at the constructs inside of the movie header. So this integration is essentially a wholesale replacement each time. So this is not what you would consider something that you need to keep historically. So it's not an incremental load. So in this case, the first activity you see here is a delete activity. And the delete activity takes in the concept of a data set. And this data set says raw movie JSON. So what is that? So let's go ahead and take a look. Here it's using a link service called My Data Lake. So this is the little storage icon here. And it's saying that the file path is in the raw Tmdb movies JSON. So I can actually go ahead and preview the data here. And you can see some JSON data comes up. If this was like a CSV or an Excel file, for instance, you would actually see the tabular representation. Same thing if it was like SQL Server or Oracle, you would see the tabular representation. But because this is JSON data, that's essentially what you're going to see. So let's go ahead and take a look at this. So this is going to be inside of my data lake in the raw Tmdb movies JSON. So this pipeline's actually already been run, but I'm going to go into my data hub, go to linked. And you're going to see that within Synapse Analytics that you're actually able to navigate into your storage account. So let's go ahead and expand my data lake here and go into the raw Tmdb. Maybe if I took my cell phone out of my pocket, it'll go a little faster, but I don't know. So here's our movies JSON. So this is the header information, and as you can see that there's a bunch of JSON files here that have been ingested, and you can preview here as well. So again, I don't have to go out and use Storage Explorer or anything like that. I'm able to navigate into my connected data sources directly within Azure Synapse Analytics. All right, so that is the data set, again, is pointing to that raw movie JSON. So every time this pipeline is run, then what is it going to do? So let me go ahead and collapse that just so we can see it a little bit better. We're actually going to delete them. Again, we don't need that incremental load in this case. So we're going to delete everything in that raw movies JSON is essentially what that's saying. So when this pipeline gets run, clears that folder out, and then the rest of the activities will essentially repopulate it. So here's The next one is a web call, and this one's actually a little bit of a exploratory, if you will, call, because with a lot of REST APIs, there is usually paginated results. So if you're going to have like 18,000 rows come back with 1,500 fields each, typically it's not going to be in one call. You're going to have page 1, page 2, page 3, page 4. So this is a web activity call, which essentially will use, and you can see there's a dynamic content here where it builds the API using the parameters passed in. It's going to do that first REST call and then introspect the results and set a variable on the pipeline to indicate the number of pages that you're going to refer to. So if I go ahead and take a look at the set variable, what it's going to do is take the response from that previous activity for the obtained number of pages, and it's going to create an array of 1 to X number of pages, so I know how many times to loop through to get another page of information, which then brings us to the for each loop. So the for each will allow me, again, for each item in this array, I'm going to execute a copy data activity. Now the copy data activity is probably one of the most common that you're going to see, especially when we're talking about that raw ingestion piece. So essentially what the copy data does is it copies from a source data set to a sync data set. And then of course remember that the data sets themselves are linked to a link service for external compute. So you can see that my source data set is this Tmdb movies discovery rest. So let's take a look at that data set. So the data set again has a relative URL that is built based off of parameters passing in. So here we have parameters at our pipeline level. We also have parameters at our data set level. So here's the parameters here. Again, every time I want to make this call, I want to make it generic enough that if we need to change, for instance, certain runs to have different parameters, we can do that. But that is what the parameters are going to be used for. So the copy data will take the source, which is the REST call for the movie header information, and then it's going to drop it into that raw movie JSON. So again, same data set that I used inside of that delete activity, I'm able to reuse again to drop the data from the REST API calls directly into movies.json. So that is essentially how that folder gets deleted and then repopulated. So let's take a step back here and talk about the linked services here just for a minute. So within Manage, you're going to see that we have linked services. And those linked services can be, again, one of hundreds of different types of connections, as well as some generic type connections as well, like ODBC, for instance. So you can see I have a link service to Amazon S3. I have one to the data lake. So again, that's the data lake where I'm storing my raw data. I have a load user. So this is another best practice when you're talking about population into your data warehouse proper. So it's basically a load user that has reserved capacity, if you will, of compute when we're talking about loading the actual data warehouse. And then, of course, there's our Tmdb API that we looked at earlier. So if I hit New here, you can see that there's a bunch. So there's Amazon RDS for SQL Server, for Oracle. There's Cognitive Services, Cosmos DB, Key Vault, Cassandra, Drill, Dynamics 365, FTP, what have you. So there's hundreds of them in here. The generic protocols, again, we're using the REST one here today, but it has support for things like OData as well as ODBC as well. So that is essentially how you would create your linked services. So let's take a look at this load user here for a moment. So you're going to see that there's different settings that you're going to enter for that connection string information. But what I want to call out here is that I'm able to use the Azure Key Vault. So when I actually deploy this environment, I don't even see the password. I actually have a Terraform script that creates the secret for me, and I never look at it. So unless I give myself explicit access to it, I don't ever have to see this password. So I go ahead and I store that inside of Key Vault, and it's going to say, well, what is the password? It's stored in DW load user, and it's going to ask, do you want to use a specific version? I just say to use the latest version. So again, I'm able to have those credentials stored inside of Key Vault and not have to disclose that password to any developers. All right, so there we go on that. So far what you've seen is we've gone ahead and we've looked at a lot of code-free ways of doing transformations, but there's also coded ways. So let's take a look here at, well, actually, let's go back one moment. Let's talk about one more code-free way. I want to introduce data flows. So a data flow is essentially a visual canvas, like similar to what we're doing with the data pipelines, but it allows you to refine your actual data. So you're able to perform transformations on your data without writing any code. So let's go ahead and go into that. So here we can see, again, similar canvas. We have a data flow here that takes our movie header raw. So that is that JSON data that we just landed. And if we take a look at the projection, so the projection is essentially a introspected schema, if you will. So I didn't have to write this. I just said import the projection. It'll take a look at the structure of the files and deduce a schema for me. So we can see that these JSON files have a page number. It has a results array, which is a complex object of these fields here. And it also has a total number of pages and total number of results. So that's repeated in every single file that we landed inside of the raw. Of course, we don't need all of that, right? So I have a flatten results activity here, and essentially what that will do is it's going to take, we want to grab this results array and flatten that out so that we can essentially refine it that way to make it a little bit more queryable. Because at this point, we don't really care about page number, total number of pages, or anything like that. So here's the flattened results, and I'm going to unroll it by the results. And essentially what that's going to do is it's going to create a mapping for us. So the results adult field, I want it to be the adult field. Results backdrop path, I want it to be backdrop path, so on and so forth. So that is available to us here. So let's take a look at what the raw movie data looks like coming in. So here we can, oh, of course it went away on me. So it's going to come in, and essentially that results array is going to be an array. So you can see that, okay, yeah, whatever, we can drill in and take a look at what those are, but we want that flattened. So at each step, I have something called data flow debug turned on. What it does is it grabs a sampling of the data that essentially your data set is pointing to, and you can see the transformations at each level. So after the flattened results, and I've mapped those fields moving forward, you're going to see that we no longer have page number, we no longer have total number of pages, and so on. Now you can see that I've actually taken that JSON data, taken the array, and now instead of an array, we actually have a flatter construct that has adult, backdrop, path, ID, original language, title, overview, popularity. Now, of course, we need to have a place for it to land. So again, I talked a little bit earlier about the data sets needing, well, store the raw data as raw data, but when you start refining, it's typically better to use Parquet format. So what I want to do is I want to refine this and store it as Parquet in the refined Tmdb movie Parquet. So this is the data set again, and it's pointing to refined Tmdb movies Parquet. So that is the sync of this transformation, if you will. So if we take a look at the data here, it's going to look very similar to what we had at the flattened results, but in this case, the destination is actually going to be in Parquet format. So let's go back to our data lake here, and you can see that we have refined Tmdb, and refined Tmdb will have the Parquet files if it decides to come up. There we go. So movie details, or sorry, movies Parquet in this case is there. So there you go. So different Parquet files. All right. So let's now go back to more coded approach. So we have non-coded. So again, kind of both audiences here. If you wanted to do everything programmatically, you have the ability to do that. But what's also nice is you can actually drop down to code, and that's typically where I like to reside. So when you are executing like the data flow activity that we just saw for refining into the Parquet format, essentially behind the scenes, what Synapse is doing is it's generating Spark code and running that Spark code on an internal cluster. And that's not something that you can control the sizing of. It'll just scale with the size of the workload. But in this case, this is an actual Spark notebook. So let's go ahead and take a look at that. So this is a notebook activity, and I can go ahead and open that. So here we go. I have a Spark notebook running directly within Azure Synapse Analytics. So the first cell here you can see is toggled with this parameters. So inside of the pipeline, you can pass parameters, as I showed you earlier. You can also pass parameters into your coded activities. So this parameters will say, I'm expecting this API key to come in, but what you'll see is when this notebook is run, essentially it'll create below this parameter cell, it'll create a new cell that'll essentially override the values with what's passed in. So what you want to do is set their default values there. So in this case, I need the API key. Global variables, again, we're going to do the same type of construct where we're going to drop the details data as raw JSON files. So that's going to be inside of my data lake here in movie details JSON, so the raw Tmdb container. We're also going to have the movie header path. So again, this is that movies Parquet. So we already grabbed our header information, we've refined it, stored it in Parquet. I want to use that data to obtain a list of movie IDs that I need to get the details for. And of course, we have the details REST endpoint, which I will construct, basically replacing the movie ID in the API and using the API key inside of that string. So essentially, I'm going to replace the movie ID. Generate a list of URLs. So what I'm going to do is use a nice parallel library called async.io, and I'm going to, for every movie ID, so here again we're using Spark to read the Parquet movie header, so it's going to actually read every single Parquet file there and grab the movie ID values, so just the ID values, and create a list of movie IDs. And from that, I actually generate the URL that it's going to be called, and then use async.io to make the actual call. So what's really nice about this library is that, at least for this one, over 360 calls can be made, and I think it takes about 20 seconds. So it's a really nice, efficient library to use. So MS Spark utils, if there's any Databricks people in here, a lot of your DB utils functions you're going to find inside of MS Spark utils. So for instance, the file system really makes interacting with the file system very easily. So you can see that I'm actually putting in the details raw path, the JSON files, and essentially doing that ingestion that way. So again, you have the coded, you can have the not coded. So if I go into my data again, you'll see that we have raw Tmdb again. We'll have our movie details, and that will essentially have the movie details JSON as well. So here's raw Tmdb, movies JSON. So that's just the basic gist of it. So if I wanted to preview these, we can take a look at what these details look like as well. So the next step along the line, again, is going to be to refine that in Parquet, and it's going to be a very similar data flow, which essentially I threw in a couple extra things in here for lookups. But really what I'm doing is, because it's not an array-based, I renamed some things, so essentially going from raw directly into sync, which is going to be the Parquet folder for movie details. So that essentially shows that first raw ingestion piece. So what's nice too is I have a curate layer. So the curate layer, I don't know if there's people here that use like Athena inside of AWS, for instance, or serverless SQL Server, but you have the ability to set up a logical data warehouse directly in storage. So this is not your data warehouse database. This is a logical data warehouse that essentially behind the scenes is going to be fueled by Parquet files. So I have a notebook here that will actually set up this logical data warehouse. And you can see that I have like a genres table, a configuration table, movie details, movie dimensions, movie genres. And I also have, for further demonstration purposes that I won't get into today, but different AI type, like recommendation engines, logic, and so on and so forth. But that's for a much longer presentation. So, but you know, I'm more than willing to share it. I could meet you on Twitch sometime, maybe. But so where was I going with that? All right, so let's go back to our pipeline again. So I have a logical data warehouse. That's where I was going. So inside of your workspace, you're going to see that there's something called a lake database. And I really don't like the name lake database. Essentially what that is if you're familiar with Spark, you can create Spark tables, for instance, and Spark databases. That's pretty much what a lake database is, but they didn't want to include Spark there because the serverless SQL endpoint also has the ability to query those tables. So they wanted to genericize it a little bit, but in my mind, it's always going to be a Spark table. But inside of this logical data warehouse, I have the ability, again, to go in, and you can use Spark. Again, just use the percent SQL magic and query it directly. But you also have the ability to use the serverless endpoint. So the serverless SQL Server endpoint is this built-in one. So I'm able to query the logical data warehouse directly using the serverless SQL endpoint. It's going to hopefully not make me a liar. There we go. But of course, I have way too many things open on my screen. But anyway, so again, this is not an actual database table. This is a Spark table or a Parquet-backed file-based table in storage. So what's nice about that is your dedicated SQL server costs a lot of money, especially depending on how much compute that you're using. So what's nice about Synapse is when you're not using it for analytical workloads, go ahead and pause that thing, right? Only turn it on when you need it. And if there's something that you need, just like a sampling of data or a sliver of data, go ahead and query the logical data warehouse to get the information that you need. So I'm going to go ahead and discard that. So the last piece of the puzzle is the actual data warehouse population. And you can see I created two data flows, one's to populate the dimensions, one's to populate the facts. I always hate the zooming in here too. I can zoom it right in. But you can see that it is, again, all visual. I have some aggregation functions in here, aliasing columns, allowing upserts, for instance. But at the end of the day, the data set is going to be my data warehouse. So inside of Azure Synapse Analytics, you have the ability to have multiple Synapse Pools. So built in is that serverless endpoint. Movies is, again, your traditional SQL Server data warehouse. I currently have this on a very puny DW100C because I'm cheap. I don't want to spend money, but you have the ability to scale that and then, of course, pause it as you need it. So inside of that schema, I have, so I can go back to, again, my data here, go into my SQL database, and you can see that I have a star schema that's already defined, has multiple dimension tables as well as fact tables. If I can expand that, there we go. So let's go ahead and see, I don't know, customer behavior. Again, this was generated data, but let's just want to show you that you can query, again, directly within Azure Synapse Analytics directly into your data warehouse database as well. So again, I was able to navigate storage, define pipelines either code-free or coded way. I'm able to query using the serverless endpoint on my storage. I'm also able to preview files, and of course, at the end of the day, we have the big powerhouse data warehouses that have the dimensions, like my star schema essentially populated in this case. So I'm doing that through data flows. All right, so let's go back to my presentation. I don't know how much time I have left. 15? Awesome. Okay, that should be perfect then. All right. Of course. All right, so this is a little bit more of, it's going to be like a fire hose of best practices that we've learned along the way. So I've already mentioned that it's always good to load data in its raw form inside of the data lake as quickly as possible. Again, we're dependent on that connectivity. We're dependent on that source system. Any dependencies that you can eliminate, do that as early as possible. So again, loading the data in the data lake first allows you to more easily develop your pipelines as well as rerun things, debug workloads, and what have you. So when loading data into the dedicated SQL pool, depending on the complexity of the transformations and the amount of data, it's always a good idea to load data initially into staging tables. So I didn't do that in this demonstration here, but typically what you're going to see is inside of your data lake, you'll have your raw, your refined, whatever number of levels that you have inside of your data lake. You can have your curated be a lake database, for instance. But when you're actually loading into the SQL pool, if you have like extremely large fact tables that you're doing large amounts of transformations to, you can actually perform transformations directly inside of your dedicated SQL pool as well. And what we recommend there is when you have these types of loads, load to staging tables first. Never, ever, ever load to a replicated table. So inside of every dedicated SQL pool, there's always 60 nodes. 60 distributions, I shouldn't say nodes, because physical nodes, you can have multiple for each. You can have like, I think there's 2 nodes, physical nodes up to 500C or something like that. But anyway, never load to a replicated table, because again, that overhead will take that data and essentially replicate it across the 60 distributions. So it's not very efficient for when it's something that's temporary for your loading. Another thing is scaling, and actually this is something that I used quite heavily this week. I was doing a large back data load into a data warehouse. But what we did was we actually scaled our SQL pool as well as our Spark pools just for that ingestion, because we knew that we had this enormous workload come in. So something that, you know, under a DW 500C, for instance, would probably take 2 weeks to do, I was able to do it overnight. So we scaled it pretty heavily, but what we needed to do was get that data in and get that data in processed fast. Another thing is something I mentioned a little bit earlier is inside of the SQL Server, you want to have that loading user. So if you just go ahead and create any random user identity inside of SQL Server, it's only going to use about 5% allocation of resources. So when you're talking about loading large sets of data, what you want to do is create a specific user for that and assign it, like, I don't know, depending on the size, if you want to reserve it like 25% of the capacity, for instance, you can do that. So again, making that loading more efficient. Another thing is, for the serverless SQL pool, is co-locating the storage with the serverless SQL pools. So everything that I have deployed right now is in East US. So what we're saying here is the storage account that you're using for your data lake, you want to keep it in the same region, preferably that you've put your Azure Synapse Analytics workspace. That's what you've deployed it to. So if it's East US, put it in the same location. Again, geographical logic there comes into play. Another thing I didn't talk about is the Cosmos DB analytical stores. So there is an integration using HTAP, so basically extremely fast integration with Cosmos DB. If you have that as a source, again, try to keep it in the same region if possible. Next thing is data lake organization. So one of the things that you're going to find out really quick is that enumeration kills performance. So on the left, you can see a couple examples of ways of structuring. So if you have sales, for instance, you can have sales, I don't know, tires, data in, year, month, day. So what we're trying to avoid here is having like one folder with 8 million files, for instance. You want to be able to have it structured in a way that, one, you can query it using the serverless endpoint easily. So if I have SQL Server, I can come in here and say, grab me, like, we'll pretend it's Parquet format, but it doesn't really matter. I want to grab like all 2010 sales figures. Because I have it structured this way, I can actually use the serverless SQL endpoint and query into my data lake for 2010, just by how I've structured the data lake organization. So what that does is essentially performs partition elimination. But at the same time, a good rule of thumb for performance is that an ideal file size is probably 1 to 2 gigabytes in size. And you also don't want to have, at maximum, have 3 to 4 times the amount of number of files as you do have processors. So again, a lot of these things run in parallel. So if you have certain number of processing powers associated with it, typically you can, from a vantage point, you can identify how many files is ideal. And of course, if you have, like as in our case right now, we had 300 JSON files come in. It's not enough really to impact performance, but say we had 18 million JSON files coming in. There's nothing stopping you from pre-processing this information as well as part of your refinements, and you can actually move all that data into a single 1 to 2 gigabyte file. That will in turn be a little bit more easier to process. Another thing is, I mentioned that Parquet is recommended when you're doing your refinements. So Parquet is an open source columnar format, so we're able to, again, query directly within it. What's nice about Parquet as well is you can actually have different partitions within the file itself. So that's what this image here on the right is. So we have our Parquet files, and you can see within data Parquet here, we have partitioning for City, Miami, New York, and Seattle. And that partition elimination happens just as I explained it for the file structures. You can have that within like your 1 to 2 gigabyte Parquet files as well. I mentioned that there was 2 different types of flavors of Parquet that you can get, that you can use. What you saw today, I used just regular vanilla Parquet files, but you also have the option of using Delta Parquet, so Delta Lake tables. And what Delta allows you to do is essentially have atomic transactions directly on your Parquet files. And it also has a full audit log of things like modifications and changes, so you can actually time travel back inside of your data lake to specific points in time, for instance, to take a look at historical data. So that is where Delta Lake comes in. So depending, again, on your use case, if that's something that you can use, I do recommend using that. Next thing is distribution. I mentioned earlier, there's always 60 distributions. You want to use round robin distribution for staging tables. So what round robin does is it just randomly provide, like segments a row into each of the 60 distributions. So there's no rhyme or reason. So typically good for staging tables. Hash distributions for fact tables is typically what you see. What that does is essentially you would identify a column that would essentially distribute logically pretty much into the 60 distributions. And what Synapse does is it will use a deterministic hash functions to assign each row to a specific distribution. So that is where that comes in. So if you have, like, if you were distributing like on customer ID or something like that, you can be assured that every row coming in for that customer ID is going to be stored in the same distribution. So there's a lot less data shuffling, if you will, behind the scenes when you're querying it. The last one is replicated for dimension tables. I did mention earlier, do not use replicated tables for staging tables for your data load. No bueno. You want to use replicated for, again, we're talking about our queryable data warehouse in this case. So if you have those small lookup tables, go ahead and use dimension tables for that, because again, when you co-locate your data in specific distributions, as long as it doesn't have to, like, if less travels across the distributions, the better. So replicated tables will be in each distribution. So because those lookup tables are commonly used everywhere, it makes sense to have those as replicated into each distribution. All right, the last one is indexing. You probably heard, and a lot of people think that clustered column store indexes is the best thing since sliced bread. And I say, it depends. So yes, it's a fantastic performing index, but at the same time, if you don't have the amount of data necessitated for the compression of that index, it's not really going to give you much benefit at all. So again, high-level data compression, rule of thumb is 1 million rows, and again, remember we have 60 distributions, so 1 million rows by 60 distributions by the number of partitions. So if you're internally partitioning your SQL tables, you need to multiply that as well. So if you don't have that much data, there's nothing stopping you from using CCI, but you're not going to see that wow performance gain until you have enough data in there. Another thing that's recommended is using batch sizes of greater than 100,000 rows up to 1 million. Again, that we're talking about just batching the data as it's coming in. Tables should have minimal update and delete operations or rebuild frequently. So the reason for this, again, is because when you have CCIs, you have that overhead of the indexing. So what we found is if you're changing more than 10% of the rows, it actually makes sense to stage an entirely different table using create table as select, make the modifications there, and then do a name swap. It's actually more efficient to do it that way because of the overhead of the indexing. So if you don't want to do an offline rebuild or have time for that sort of thing, again, take a look at your workloads and see how much data is actually changing. It might actually make sense to create a new table and then swap it out. Clustered index may outperform CCI when you're looking up a single or a few rows. So if your queries are typically, get me this order ID or get me, single rows, even though you might have the amount of data necessitated for a CCI, if you're only pulling those single rows or very few rows, you'll find out that CIs, like clustered indexes, will actually outperform the CCIs because you're only retrieving small amounts of data. All right, heap we talked about. Heap is essentially the non-index index, so it's best for staging tables. And then, of course, non-clustered secondary indexes. You can evaluate when you're querying your data afterwards if it makes sense to add an additional field into an index to improve your query performance. But again, too much of a good thing can be a bad thing. So more indexes you add, the more overhead that you get as well. All right, so let's talk a little bit about performance best practices. We have Spark in this case. So Spark inside of like the Python libraries out there are numerous. But one thing that I'd like to emphasize is when you're using Synapse, go ahead and leverage the specific Microsoft developed connectors. So the difference between these is typically most like normal Python libraries, they're very synchronous in nature, whereas Microsoft developed these other connectors for like Synapse SQL, Cosmos DB, Synapse Link, and Azure SQL. It's actually developed to take advantage of the parallelism out of the gate. So go ahead and do that. We already talked about using Parquet format for levels of refinement. We talked about delta lake. So again, ACID transactions, as well as that history log, so you can time travel back. We used a lot of schema inferring here. So if you're using Spark, you have the ability to create essentially a schema for your data sets. So go ahead and use those wherever possible. Inferred schemas are typically not perfect. So you want to pay attention to things like field sizes, field types, and so on. So typically you're going to get better performance if you say, no, this is the data that I want, and another attractive nature of that is you can also grab a subset of the fields that you're interested in. You also want to use data frames or data sets over RDDs, avoid user-defined functions. User-defined functions, again, are that single threaded performance, so UDFs don't run in parallel. You want to cache repetitive work, so if you do read essentially a large amount of data inside of your data lake, for instance, inside of Spark, use the cache mechanism to make sure that that read hit only happens once, and avoid expensive operations. And again, here's some that are, again, that single-threaded type function, so collect, count, distinct count. Use koalas versus pandas. Again, pandas is synchronous, whereas koalas, when I say synchronous, I mean like single-threaded. Koalas, again, takes advantage of parallelism, and I think they're probably up to about 90% parity with pandas now, so a lot of good movement going on in the community there. There's also something called Hyperspace Indexes, and that essentially is indexes that you can put on top of your storage. So it's similar to as you would create an index inside of your SQL Server tables, you can actually create indexes on top of your Parquet files, for instance. So what that does is, again, allows you to get incremental, like huge performance benefits, again, depending on how you're using your data lake. So with that, that was what I had for you today. If anybody has any questions? Nothing?
Get you on Slack afterwards. So.
All right. All right, so I'd like to thank you so much for coming out today. If you do have any questions, feel free to come up to me anytime or reach out to me on Twitter or on LinkedIn, and I hope to see you later on today.